All right. I'm really excited about this. I've already been through this with him, and I'm pretty excited for all of you. John Seymour. What can I tell you about John Seymour? He's an adjunct professor at Clemson University. He also is a consultant, also known as the infamous John the Math Guy. He holds over 31 patents on color measurement devices. And man, he's provided over 100 presentations and papers in his 30 plus years in the printing industry. So with that, I'm excited to introduce Mr. John Seymour, and we're going to have some fun here today, but we're going to really geek out. So, John, take it away. It's all yours, buddy.
Hey, thanks, Joe.
You bet.
I like the music that you started out with. That was a good selection. Good selection. Maybe we should just skip the webinar and groove on that music. What do you think?
I've actually gotten comments in the past, but no, we'll just carry on. We'll play that same playlist on the 25th for Alyssa's webinar.
Okay, you need to get, I'm going to Kansas City, here I come. You need to get that one in there.
We'll work it out, but I like you with the microphone. I think it's so much classier.
Yeah, this is a Shure SM58. It is like the microphone for stage bands.
All right. Well, you go ahead, John. Let's roll.
Okay. I am now 65 years old, which means that I get a chance to be a curmudgeon. And today that's what I'm going to do. I'm going to be a curmudgeon about CIELAB. I'm going to talk icky stuff about it. I'm going to say bad things about it. And I want to start off just saying that CIELAB is the backbone of our industry for color measurement, control, specification, the whole bit. It's vitally important. We shouldn't give it up, but we need to be looking at replacing it. So CIELAB is icky. Do we have any other choices? This talk was started inadvertently by this fella here. You may recognize him. No, he doesn't play big on Sex and the City. And if you listen to him talk, you may think that he is a late night jazz radio announcer because he's got that really smooth voice. But he's a very desired speaker because of what you see on the right-hand side of the screen. He makes software that allows us to visualize color in color space. Look at the three-dimensional space, and by rotating it, zooming in on it, we can, in this case, we're comparing two gamuts, the size of two gamuts. We can see what basic colors are in the gamut and what are not. This is fabulous software to get your intuition going about how color works. Anyway, he spoke at a couple of conferences last fall. One of them was an FTA conference, and the other one was from a competing organization whose name shall not be mentioned in this webinar, obviously. But in just kind of a side note, he had been playing with this new way to compute color, and he showed a couple slides on that, showed some neat things that it did that CIELAB doesn't do, it does differently than CIELAB. And strangely enough, I got 3 questions from 3 different people about that, saying, hey, what's up with this? They were asking me, what's the jazz about JZAZBZ? JZABZ, it's really tough to say. I think that I need to talk to the marketing people of these guys for this color space and say, you need to name it something that is repeated, that you can say, that trips off the tongue. Calling it jazz space would be cool. That's what I think it should be called. But anyway, I got 3 people in the next week saying, John, what is this? And I mean, I rarely get 3 people talking to me in a month. So to have 3 people asking me one question, one of them is the guy that just laughed there. That's Joe. He was sitting next to me. Not virtually. He was sitting virtually next to me when we heard Steve Upton use this. And he's, John, what is that? But anyway, 2 more people had asked me about it. So clearly there's some interest here in what's going on. I want to fill that out a little bit.
Yeah, but he also introduced the topic of color porn, which is very interesting to a lot of people.
I will neither confirm nor deny rumors that I have been involved in that. Here's the paper that started this whole thing. This is from 2017, just 7 years ago. Perceptually uniform color space for image mapping, blah, 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 blah. And there's all kinds of authors, and they're from China and Pakistan. And okay, so a perceptually uniform. Okay, I'm not going to go into detail about what this color space is, but I want to talk generally about the family of color spaces that this belongs to. The story starts back with Frederick Ives in 1907. Frederick Ives was a inventor, very smart guy. He he contributed to color photography. He was one of several people who had come up with means for taking color photographs back in the late 1800s. And in 1907, he came up with a color meter. And I think maybe this might have been the first one. It has been long recognized that a universal color meter capable of measuring all colors and expressing them in numerical terms must be based on the principle of Clerk Maxwell's color box. Well, 1870, James Clerk Maxwell had developed this thing called the color box, which was a huge thing. Some people called it the color coffin. It was that big, but people would look in it, and he had a prism in it and knobs and stuff, and it was very scientific. And he was using it to try to understand how the human visual system works. How is it that we can perceive color? So he's trying to quantify that. That was not technically a color meter. I think the first color meter was this one by Ives, where the goal was to be able to measure, take a sample and put numbers on it as to what color it is. Here's a diagram from his first paper. He wrote another paper in 1907. He filed a patent in 1907 on substantially the same thing. It looks like a telescope because basically that's what it is, a telescope that a pirate might have. On the far right-hand side is the eyepiece, that's where you would look through. And on the left-hand side, the user would put two pieces of things. They would put a white piece of paper, for example, that's going to be essentially a white reference, but we'll get into that. And on the top, we see a blue sample, which is whatever it is that we're trying to measure. Now, the cool part about this is that there is a diffraction grating on the far left-hand side of the instrument. A diffraction grating will separate colors out into a rainbow. And here we see there's an aperture that lets through red light, there's an aperture that lets through green light, and an aperture that lets through blue-violet light. And each of those apertures has a knob on it that allows them to open and close that aperture. In doing so, the user is expected to be able to adjust those apertures in order to match the color of their sample. And when you get done with that, the size of those three apertures stands as a proxy for whatever color it is that we're talking about. Now, that may seem like an odd way to specify or to measure color. I mean, we're used to using CIELAB. So L star, A star, and B star seem to be the things, but that's okay. So this seems odd, but actually it's not quite as odd as you may think because we actually use the system today. Here we see the guide, the color guide from Clemson. I don't know if you've heard of it. Clemson is the football team, but the football team actually started, they were making too much money, so they just decided to start a college to, keep their nonprofit status. So there's actually a college associated with this, and they have Clemson orange is the big color, but look down here. They specify the color in terms of RGB. Now, it's another topic, but they also specify CMYK and Pantone colors, and that's not a good thing to have colors specified in different ways. But that's a different topic. The idea here is that we still use this idea today to let those numbers, 245, 102, and 0, let those numbers stand proxy for a color. Those three numbers will identify kind of. Of course, it depends on somebody's monitor. Every monitor is going to render color a little bit differently. But the idea is there that today we are still using this technique developed in 1907 by Frederick Ives to measure and specify color. His wasn't the only colorimeter that was made this way. Here's one that was made by Guild in 1927. This is when it first came out. It was being offered for sale by Adam Hilger Limited, which is a company that is still around in England. It's called the trichromatic, that means it has three primary colors that it's mixing. Colorimeter means it's a device for measuring color. And that is different from the colorimeters that we know today. Today, the colorimeters have three filters in them. They don't mix colors the same way as this, so colorimeter has changed its meaning. But okay, so at this time in the late 1920s, we had at least two different manufacturers of trichromatic colorimeters. What was the response? Did people like these? Were they being used? Well, here's one quote. This is from the Journal of the Optical Society of America in 1921. This is a paper, Systems of Color Standards. You can think of that as how does a brand owner communicate the color to the manufacturer of that color? That's what the topic is. Standardizing of color can be done either by an instrument, as we've talked about here, such as the colorimeter, or a standard composed of colored cards. Now we're familiar with that. Some people, I'm guessing on the phone, on the webinar today, have a copy of one of these called the Pantone book. Sherwin-Williams has one. There is the NCS one. You can buy one from the Munsell Corporation. All of those are these type of card standards that this author is talking about. But now let me get to the bold part, because this is when A. Ames, I don't know if that's a man or a woman, says, as any instrument is too complicated for general use. Ooh, only those standards composed of colored cards will be considered in this paper. So these trichromatic colorimeters, forget about it. Here's another book. This is a book called Color and Applications that came out in 1921, at least the third printing. Okay, that means this was a very successful book. Color and Applications. Trichromatic colorimeters can hardly be considered, this is not sounding good, can hardly be considered more than approximately comparative and of limited usefulness. Ooh, you like that, Joe?
Yeah, it's funny.
Yeah, I mean, this is not high praise, owing to the fact that the method is not sufficiently analytical. Oh, okay. Let's take a look at another textbook. This is one from Martin and Gamble from 1926, Color and Methods of Color Reproduction. With typical errors on the order of 2 to 5%, that's kind of big. Trichromatic colorimeters are just significantly good to make the instrument of practical use. Again, high praise. They're almost good enough. Yes, I want one. Where do I sign up? Raffi, this is in a paper in the magazine Science Progress. Many industries, if they were denuded of all color, could no longer exist. Now, that's a powerful statement.
Yeah.
And Henry Ford might disagree with that. Joe, do you remember what was going on with Henry Ford at that time?
I do not. I was working.
Yeah, I know. He came out with a Model T, and
That whole thing.
in order to make the production go faster, in order to make these as efficiently as possible, he made the decree that a customer can have a Model T in any color they want, so long as it's black. Kept that up for about a decade, so he managed to have an industry that was denuded of color. But eventually, his competitors took that as an advantage, and they played against that by offering different colors. And eventually, he had to give in. But continuing back here, a lot of industries rely on color. Almost everything that we buy has color injected into it at some point. Despite this importance, such industries have no simple comparative means for measuring color. 1926, this was stated. And here's another quote from that same article. Any color can be specified accurately by 3 colors, in other words, a trichromatic colorimeter, yet no method of specifying color in this way is in use. Now, that's probably too harsh of a statement. I think it's maybe a little bit, there were probably some that were being used. But the thing is that it wasn't really a big popular product. The situation in the 1920s is that there was a big need for color measurement. Trichromatic colorimeters were a way to do that measurement of color, but they were not an ideal solution by any means. They were too expensive, too cumbersome, too bulky, and the measurements were sloppy. There wasn't an awful lot of inter-instrument agreement. Now, here's a poll question for everybody.
Oh, I better get busy.
I've got 2 graphs here. The one on the right, we see it, the one on the left, I'm sorry, A, is the a paper from Troland. It shows 3 graphs labeled red, green, and blue. And the one on the right is the tri-stimulus specification of the spectrum according to the 1931 blah, blah, blah. Which one of these represents the eye? And I see some people have typed that into the Q&A. That's not the right place to put it. There's some way.
Yeah, that guy's trouble though.
Oh, tell me about it. Yeah.
Well, there you have it, John. It's still coming in, John.
Okay. I see I'm not allowed to vote.
No, you're not. You just get to watch, but they can't see the results as they're coming in like you and I can. They can't see them until I share them, and I'm going to do that momentarily.
I'm on pins and needles here.
Are you? All right, here we go. Ready? We're going to share those results. There you have it, John.
Okay. It looks like the majority, 65%, 2/3 of people, said that B represents the human eye. I expected that. That's the wrong answer. The human eye has a spectral response that looks a lot more like A. Let me talk about that a little bit more because there's a story behind that. But first, we'll ask another quiz.
Uh-oh.
In 1931, the CIE decided on one or the other course of action. Either they decided to emulate the obvious choice of the human eye when they decided to put together this tri-stimulus standard observer, the 1931 stuff. Or B, did they decide to emulate a persnickety, expensive, hard to use, and inaccurate instrument that was obsolete 70 years ago and can only be found today in museums? Which did they decide? Which way did they go? Did they decide to emulate the eye or the trichromatic colorimeter?
Ready? You ready, John? You ready for the results?
Yeah.
All right, here we go.
People figured that they decided to emulate this instrument. And that is the correct answer. Rather than emulate the human eye, I've read through all of the papers and I've tried to find papers that said, what is their mindset when they're doing this? It didn't seem to occur to anybody at the time that the way to measure color is to try to emulate the human eye. What they were trying to do is emulate this instrument that they realized didn't work so well. They wanted to make it work better. Their goal, when they came up with the standard observer back in 1931, when the CIE did this, their goal was to emulate that trichromatic colorimeter. They defined what they called the standard observer, and they did that by having 17 British men come together, all men, all British, and there's only 17, and the results were averaged between them to get the standard observer. They also decided to standardize on one shade of red, green, and blue for this colorimeter. It may not be quite obvious, but you have to have the same red if you're going to be able to compare two instruments. So they decided on a set of red, green, and blue that would be the standard primaries for this hypothetical instrument. The primaries they chose were actually impossible to make, not hard to make, but impossible to make. So this is a virtual instrument. It doesn't exist. It can't exist. But the thing is that they have standardized it. And the idea is that if you start off with a spectrum, you measure your sample with a spectrophotometer, which was available at the time, and they were fairly decent, kind of expensive, but they were available at the time. You would use a bunch of math on the spectrum, and as a result, you would get a prediction of what somebody would measure, the red, green, and blue values that somebody would measure if they were to use this standardized instrument. They were called the tri-stimulus settings. Tri meaning three, stimulus meaning primary stimulation. So that was, I see there's a question here. Joe, you want to read that?
Well, I sure will, John. This is from our friend Bill Pope at RIT. He's always wondered why the work done in 1931 has never been redone. If there's so many flaws with that data, why has no one looked to more accurately model the 2-degree observer?
Yeah. Well, of course, Bill knows that there was a 10-degree observer that came out in around 1960. So slightly different experiment, but the same thing. Why has nobody redone it? In around 2000, there was some work done at RIT. I don't know, Bill, if you've heard of the RIT. It's a college in Rochester. Bill works there.
He works there.
There was some work done. I'm not remembering the name of the guy. I'm sorry. I can get that to you. But they had very accurately measured like 100 people, and they came up with a model for what the cone functions are, the 3 cones in the eye, what the spectral response of those is, which depends on a number of factors. Particular, one of the big ones that Joe and I are aware of is that the lens in the eye yellows as we get older, which means, yeah,
yourself.
And I mean, I got up this morning and my muscles hurt and I had to stretch, and oh my God, it was hard to get up in the morning. I noticed that my body is getting older, but I never noticed that my the lens in my eyes have yellowed. So, but that happens. The eye is adapted to it. The thing is that Joe and I see color a lot different from the young guys, the young folks here. So,
So, John, Mark
yeah.
Sandworth just chimed in. He also probably has yellowing eyes.
Yeah.
Roy Burns at RIT was the person you were referring to.
Roy Burns was the supervisor. There was another fellow who was the lead author on that. But yeah, Roy Burns was involved in that. Thanks, Mark. I don't remember the name of the other guy. So, getting back to the story, in the 1920s, there was a fellow by the name of Elliot Quincy Adams. 1923, he wrote this paper with this diagram in it. This diagram is a neural network, so to speak. And I think this was a landmark paper. I am so impressed with this. This was so prescient. It was forethinking. Great stuff. I really like this paper. 1923. What he decided, this diagram kind of summarizes the whole paper up. This is a theory of color vision. This is how it is that we see color. On the one hand, on the left-hand side here, we have red, white, and blue cones. Those little triangles represent cones. And that is the trichromatic color theory. This was first described by a fellow by the name of George Palmer in about 1700. Later on, Thomas Young, Helmholtz, all of them were proponents of the idea that the eye has three different sensors that can measure color. There's three different types of sensors that are responsive to different parts of the spectrum. That idea is called trichromacy. On the other hand, there was an argument going a different way. Back to Leonardo da Vinci. Leonardo da Vinci said that we can characterize colors in terms of where they fit on the spectrum from green to red, where they fit on the spectrum between yellow and blue, and where they fit on the spectrum between white and black. Once we have specified a color in terms of those three axes, I'm putting words in his mouth. I'm putting a lot of words in his mouth, a lot of modern language. But that purportedly, that was the idea behind it. That idea, of course, since it was developed by Leonardo da Vinci, it has been called Hering's color opponent theory, after Ewald Hering, who around 1860, 1870, espoused this idea again, saying that we have these three sets of color opponents. That doesn't seem to jive very well with the idea of trichromacy. So this paper from Elliott Adams, added to the cones, said they feed into this neural network. He didn't call it that. That's what we would call it today. That does some computation. And we see there's one little star here that has an R in it. That's the red to green component. It's computed in the neurons by subtracting red from the white signal. I should mention red, white, and blue. We would call them red, green, and blue, which is not entirely accurate either. White was, I mentioned that his middle name is Elliott Quincy Adams. There's one rumor that says that he was the great-great-grandson of John Quincy Adams, and that's why it's called red, white, and blue. That's all probably bogus. Urban legend that I'm sure has made its way around TikTok for a long time. But anyway, so we have the color opponents on one side, we have trichromacy on the other side. The two were married in this paper, and that's what, I mean, this settled some arguments that were happening, but the bloody arguments that were happening in bars and every time there was a color scientist convention, they'd get together in the bars and they'd argue about trichromacy versus color opponent theory, and this paper resolved that, or at least it should have. Unfortunately, I did a little research on Google Scholar. I brought up that paper from Elliott Adams, A Theory of Color Vision. I said, Google, tell me how many papers cited this paper. And I see there are 3 papers between the time this paper came out and 1941. 3 papers that talked about this.
Wow.
So, yeah.
Not much airplay.
Yeah, not much airplay. Did you read it, Joe, when it came out?
I did not. No, I'm sorry, John. I feel dirty. I did not read it.
Yeah, well, I'll admit I didn't read it either. So, what does that say about us? I think I would nominate this as the greatest color science paper that nobody ever read. Well, I set a date of 41 because I knew that in 1942 he did a sequel to this. And his sequel did get a lot of airplay. And this sequel actually led into the development of CIELAB. I'll explain that a little bit more. But we see here 2 diagrams. On the left is from his 1923 paper. On the right, we see his repurposed diagram. He has taken that same diagram, the same drawing, and he added some stuff to it. One thing that he added to it is this right here, X, Y, Z, X bar, Y bar, and Z bar. Those are the tristimulus functions. In other words, what he did is he said, well, let's not base this on the cones. We have the 1931 Standard Observer. We have an official definition of how we measure color. I'll just use those instead. Everything else he kept the same. He added some math to it. But there's a subtle thing that happened here. And I'm not sure he knew what he was doing when there's a very subtle thing that he did, is he made the same mistake that we made long ago in those question and the polls that we took, where we showed that people thought that these tristimulus functions are actually the response of the eye. He conflated those two. He conflated the tristimulus functions, which were designed to emulate this trichromatic colorimeter, with the cone functions, which emulate what happens in the human visual system. I've read his papers very carefully. I don't see any inkling that he had knowledge of that differentiation. And I've read papers since then, and there seems to be very little recognition that that happened. The other part of his paper, this is the part that is like the quintessential results from this paper. He has a graph here of this, looks like a spider web. These are the Munsell, this is the Munsell renotation data. This is the colors that were decided. I need to back up a little bit. Albert Munsell came up with the Munsell color system back in the early 1900s. It was a wonderful system because not only did it have theory behind it, the hue, value, and chroma, the kind of stuff we think about in terms of color, but it also had a physical standard. You could buy the Munsell book, and that would allow us to communicate color with somebody else. Bill Pope could buy a copy of it. I could buy a copy of it, and that's still available today for about $1,100. We could both buy a copy of it. We could open up the page, and I say, hey, this is the color that I want. I could specify it, and Bill would be able to understand exactly the color that I'm talking about, even though he's way 500 miles away from me. So that was a great.
Too.
What's that?
He's a lot colder too, I'm sure.
Yeah, it's in the 40s here today in Greenville, South Carolina.
Balmy.
Yeah, balmy. Yes. So we have this this diagram here where we took the Munsell renotation data. Let me explain that now. About 1938 or so, the Optical Society of America put together an initiative, and they said, you know what? The Munsell color system is really good, but it's not exactly perceptually linear. The distance between colors isn't exactly what we want. There's some hues that are different. We need to futz it around, move the colors around a little bit. And they took a whole bunch of observers. I don't remember how many people there were, but there were over 1 million observations where people said, okay, we've got 3 colors here in a line. This one needs to be just a little bit darker. That one needs to have a little bit more reddish hue to it. They made those assessments, and as a result, they came up with a Munsell renotation data, which is, or was at the time, the best version of what color space should look like, the best positioning of all the colors. That's the data that went into this chart. So we have one set of data, which is purely visual data of painted samples. And we have this, some math that was done. A spectra was taken of each of those colors and converted into his color space. And look at that. It looks fairly linear. They lay out very nicely. And people looked at that and they said, whoa, that is so awesome. It was cool. This paper from 1942 became the Adams and eventually the Adams-Nickerson. Dorothy Nickerson got involved in this as well, and she did a great job marketing it and improving on it. Adams-Nickerson color space became one of many standards that was available for many decades after that. So this paper did get airplay, and it does deserve to be in the annals of color science. But I'm going to point out one little thing, that red, we think of red as a primal color, as a very basic color. It is like, the first color that people think about. It was the first color beside white and black that got introduced into nascent languages. Red is not on the horizontal axis. And red was also that color opponent thing from his 1923 paper, the color opponent things. One of the sets of color opponents is red to green. So you would think that red would be on like a horizontal axis and green would be just opposite that. And that's not the case. Red does not appear at that axis. Purple or violet, he calls it reddish purple, is what's on that axis. And You would think that maybe he would have done some stuff to make that happen, but he didn't.
Oh, come on, math guy, math dude. Isn't that red line a little curvy? Shouldn't it be straight? Are we hooking around here?
Yeah. We look at that magenta line and it does look very straight, but some of the lines in his don't follow the curve exactly. What that means is that in his color system, ISO hue is not correct. In other words, if you were to find two colors that had the same hue in his system, according to his calculations, they may not necessarily have the same hue uh, in the to the perception, to somebody's vision. That's a point I want to hang on to. Thanks for bringing that up, Joe. I do appreciate that.
Oh, you bet, John. Oh,
So let's ask the question. In CIELAB, did they fix this? The hue axis, excuse me, the A star axis, right to left as we look at a A star, B star diagram, does that A star axis point to red? Is it green? Is it yellow? Or is it magenta?
ooh, the answers just are not flying in as quickly as they were earlier, John. You're making people think.
Yeah. And there's four choices.
Yeah, yeah.
A star axis points where?
Okay, well, I think we got quite a few here. Give it another second, John.
Okay.
Bring up the results for everybody to see. All right. There it is.
Oh, I'm impressed. We have a well-educated audience here. It does point toward magenta. So, did CIELAB fix the position? According to several websites that I've looked at, these are websites from spectrophotometer manufacturers in our industry. From the Konica Minolta website, A star is the red axis. And from the Teshcon website, red-green chrominance, A star. And from the X-Rite website, A star denotes the red-green value. So these websites are telling us something that is just a little bit wrong. And to prove that it's wrong, here is from ISO 12647-6, which is the Flexo specifications, the process control for Flexo colors. It says the magenta has a hue angle of 357, which is just a few degrees short of 0 degrees. In other words, that's where A star points. A star points pretty close to magenta. Now, I wrote a paper on this to try to understand why it is that this mistake, it's not a huge mistake, right? We've lived with it, but why did this happen? Why doesn't it fit the Ewald Hering's idea of color opponents? Here I have the Munsell colors, and we see that they are the Munsell red colors. 5R means red. The hue angle of those, lots of data there, but basically all of those red dots are somewhere between a 20 and a 30 degree hue angle. So red, according to Munsell, is not at 0, it's at 20 to 30 degrees. And I wanted to know why. My supposition at this point, the CIE decided to emulate a trichromatic colorimeter. Elliott Adams, in his paper from 1941, followed suit to emulate that trichromatic colorimeter and use the standard observer. CIELAB inherited those functions from Adams. The CIELAB equations are all based very much on what Elliott Adams came up with in 1942. CIELAB emulates a device that no longer exists rather than emulating the human eye. And I think that's the reason why. And to do that, to show that that was the case, I invented a color space of my own. And I said, what if Elliott Adams had said, let's use the cone functions. Let's use the response of the human eye, and we'll do the same sort of calculations. And what we see is superimpose this mesh that's on top of this, the light green mesh. That is what CIELAB maps to on this new color space, A sub C, B sub C. And we see that the axis here for magenta is off here, and the magenta or the red axis is here. So a red axis according to my paper. So if Elliott Adams had done this differently, if he had realized that the cone functions were not the same as the tristimulus functions, if he realized that, then red would point where we would think it should. Yeah, big deal. Not a big deal at all. But let me show you a problem that is a real problem that we still deal with today. This spidergram is the Munsell renotation data at a value of 5. That's roughly an L-star value of 50. So mid-gray kind of colors. You'll notice that those are curved lines. Each one of those represents a family of colors that Munsell renotation data had decided is the all of the colors that belong to 5R or any particular hue family. And they're curved.
So this is where we get hooking.
Yeah, this is one of the causes of hooking. And in particular, consider the case where you've got a huge gamut device. You've got an image that's been purposed for a huge gamut, and you say, I want to print this on a device with a smaller gamut. What do? It's like you let the air out of the balloon. So all of the colors, just you reduce the chroma on them. You don't change the hue on anything. You change the L-star value a little bit, but basically you just make the balloon smaller. And you think, well, you know, if CIELAB is worth its salt, everything is going to come out. We're going to have a smaller gamut image, and it's going to look good. But I found a paper from Nathan Moroney in 1990. Nathan Moroney is at HP, still there. Brilliant guy. He noticed that that doesn't work, particularly in the blue area. Over here, there's a shift. And there's a shift that goes in one direction. That hook happens. In other words, as you change the gamut of a blue color to a smaller gamut, you're going to shift to the purple. Or maybe I said that backwards. It's a problem. We want that to work. Now, people are doing it. There's software that does this, and somehow it makes a correction. But I'm thinking that there's other places where the hue shifts the other way around. So it's not a simple problem. All of these are pointed, curved in different directions.
Yeah, 1 second there, holy hue guy. Mark Mazur's confused, so we have to stop right here.
All right, I don't want Mark to be confused.
Those 17 British men were asked to mix the amount of red, green, and blue light required to match a specific color. As he understands it, that is where X, Y, and Z originate. Why is that not representative of the human visual system?
It is representative of, I agree. It is not the cone function, though. That's the difference, is that they tell you something about the human visual system. They tell you something about the cones. And to be specific about it, the cone functions are a linear transform. You can multiply them by constants and add them together to get the cone functions, but they are not the cone functions. The cones do not have that response. The X bar function is bimodal. It's like a two-humped camel because it's got the two bumps in it. There's nothing in the human visual system that has those two bumps in it.
Interesting. Well, holy hue shift, math guy. That sounds darn inconvenient. Isn't there something we can do about this?
Oh, man, I wish there was. Well, I have come to the conclusion that the reason why we have this problem, the reason why we have the hue shifts that don't reflect what we don't predict hues that are the same as what the human eye would see, the reason has to do with the same thing that I've been harping on here, that if Elliott Adams had decided to use the cone functions instead of the XYZ functions, we would not have this. If CIELAB were based on the human visual system rather than based on trying to emulate this trichromatic colorimeter, then this problem would never have existed. Now, I'll bring up another problem that is well known. That last one was maybe not as common, but this one we understand that delta E in CIELAB, the delta EAB or the delta E76, the Euclidean difference formula that is used to from 1976 to measure color difference, which is important to tolerancing, which is critical to tolerancing, which is the reason why people put so much effort into making CIELAB. Delta E doesn't work very well. It does basically, CIELAB is not a perceptually linear color space. Well, it's kind of, but it fails by a factor of about 10 to 1 in predicting how far two colors are apart. This was noticed even before CIELAB came to existence. In the Adams-Nickerson 40 color space, he noticed that looking at tolerancing data from real people, looking at color samples and saying, yes, that matches, no, that doesn't. He looked at that kind of data and he noticed there's a pattern to the mistakes that were being made by the software. And the general problem, if you look at it broadly, is this. Here we see that toward the center, these tolerance ellipses are very small and they're circular. But as you increase in chroma, as you move away from the gray, these tolerance circles turn into tolerance ellipses. They elongate, and they elongate in a way that the major axis of these ellipses is always pointed toward gray. Hang on to that thought. So basically, he said, I can fix this. I can put some math in it. I can look at the chroma, and I can, pardon?
No, I'm sorry, nothing.
Okay. All right. I can look at the chroma and I can adjust the size of that tolerance ellipse based on the chroma. In other words, I can change from the normal way of computing the difference between two colors. I can change from that to something that's a little more complicated, but it's going to match reality. So he made this systematic set of equations to fix that. It was tweaked later by David McAdams, not to be confused with Elliott Adams, not to be confused with David McDowell. David McAdams was a pioneer in color science. In 1980, he tweaked this to a color difference formula called JPC79. JP Coates was a thread company, and that's where it got named from, based on 1979 data. So we see a string of different color difference equations. Delta E JPC, Delta E CMC, which was based on JPC, and this one became a standard in the textile industry and is still around today. Delta E BFD, which does not mean big frickin' deal. It means Bradford, as in a college in England. And then a bunch more, finally ending up at Delta E 2000. The idea is kind of like I think of the analogy of the Mercator projection of the map of the world. Here's the globe. If I take a sheet of clear plastic and wrap it around in a cylinder and look at it, project the globe onto that, I get the Mercator projection, which makes Greenland look absolutely huge. It's much, much, much bigger than what Greenland really is in this map. So the solution to that problem is that when we sell rulers in Greenland, we're going to make them a different size. That way they'll measure color and or measure differences in distances, and it'll all work out. And that's basically the idea. Rather than fixing the map, rather than looking at the map in a way mathematically that we can measure distance well, we're going to sell rulers that depend on the size of wherever you were at. So it seemed like a really good idea at the time, but I don't think so. We got this duct tape on these leaky pipes. I think Brad said that this picture was taken from his kitchen. My kitchen has looked like that sometimes too.
Yes.
Now we take that there's another leak that showed up later on. This is tolerancing data that had been collected from a number of different places. We see that most of those ellipses point toward gray. But then if we look down in the bottom in the blue region, just above the A star mark here, we see some of them that are tilted very significantly away from the center. So somehow we need to fix that. They decided that they would apply some math to it. This is the second ugliest equation known to man. The American Mathematical Society just announced that this is the second ugliest equation, the set of equations to compute delta E 2000. And we see that it has this rotation. The tolerance ellipses, they're not ellipses anymore, I should call them ovoids, are tilted just a little bit in order to accommodate, to fit better with that data. So they had a leaky set of pipes, they put duct tape on it, which is the Maclaurin color difference formula family, and then they put a pot underneath that in order to catch any drips that came. Oy, what a mess. It seemed like a good idea at the time. I want to bring up a different image. The image on the left-hand side is the one we looked at before of the spider legs that are hooking a little bit. And look in the blue region here, look in the blue region here. Oh, I wonder, maybe if somebody would have decided at some point in time, if somebody would have said, gosh darn it, maybe we should base this on the human cones rather than on this tristimulus functions, maybe that would have fixed the problem. So my heresy, the tristimulus functions instead of the cone functions is what caused that rotation of the tolerance ovoids. The rotation correction was put into delta E 2000, and that complicated patch was a complicated patch to a simple problem that could have been solved if we just would have used the cone functions in the start. And I think there's also other hue angles that should have been corrected in delta E 2000. Should, as in, gosh darn it, that was a bad idea, but it would make things better if they had. And the rotation probably depends upon where you are in height. Anyway, other issues with CIELAB. Changes in CIELAB when you change the illuminant. If I measure something under illuminant A, which is the incandescent light bulb versus D65, I'm going to get a different set of L star, A star, B star values. And I could ask a poll here, but nah. The question is, does the difference in the CIELAB values from one illuminant to the other, does that reflect the actual perceptual difference? And I wrote a paper saying, no, most of the difference is because of this mistake that was made using the tristimulus functions. Here's another one. I mentioned before that Joe and I have yellow lenses. How do we emulate that in CIELAB? If we had based it on the cone functions, we could say, well, Joe's cone functions suppress the blue light a little bit different, and this is how he might see color. I don't know if there's anybody on the line here that is colorblind, but if you're colorblind, you may want to have some idea, or if a designer wants to know how somebody else is going to see color, how they're going to see color difference, we don't have a way to do that. But if CIELAB had been based on the cone functions, we could adapt those cone functions to what they are for some individual, and we could predict what they're going to see. Color differences at different brightness levels. All of the work that has been done has been at basically viewing booth levels, 2000 lux. We don't have a prediction of what's going to happen if we look at 100 lux, if we look at color differences. So to me, the biggest mistakes in colorimetry, in 1931, they decided to use XYZ instead of the cone functions. In 1942, the second mistake, Adams switched horses. He originally had based this on the cones, and he changed over to the XYZ functions, unwittingly perhaps. In 1971, Maclaurin put this duct tape on delta E. Rather than fixing the color space, he used a Band-Aid to fix it. And in 1976, they continued using the XYZ. When they came out with LAB, the CIELAB function equation, they continued to use, they based that on the XYZ functions, which was what I think is the fourth mistake that was made. And in 2001, they added duct tape to the duct tape with this color difference formula. So my short summary, friends, Romans, color scientists, lend me your eyes. I come to bury CIELAB, not to praise it.
Well, golly gee, John, the math dude, isn't there an alternative to CIELAB?
Thank you for asking that, because I was just thinking about that. We talked about the jazz color space before. and that came out in 2017, but it was not the only one. It is based on the cone functions. And here I have a list of all kinds of different functions that were used. Hunt came out with one in 95 and blah, blah, blah. There's the CCAM series, which is the CIE has ratified these as official, and various others. One most recent one is CIELAB, which is a very, very simple function, which I like, but it may not emulate the eye as well as it could. We have a lot of different options, and I think what has to happen, the only thing worse than having no choices is having too many choices. I think the problem is, or what we need to do is we need to get together, put our heads together, look at these. I do not claim to be an expert on all of these. Look at these very carefully and see how they apply to our industry and make some recommendations about this is the color space that we should be using to solve the problems that we actually have. I would like to thank you for taking your time out of your busy Friday. And if you need to or want to contact me, my name is John Seymour, and there, John the Math Guy, john@johnthemathguy.com is my email.
Yeah.
And if you want to say something bad, I would suggest emailing Joe.
Yeah, that always works, right? Folks, I just want to say, you know, many times we at the FTA get the requests for John's presentation or whatnot. I don't have it. As you can see, John's broadcasting from his computer. So if you want more information, please contact John direct, and he will help you out. I just have a couple other things. You know, John, there is one question, and it's a good one. So what now? What to do?
Yeah, Sergio, that's a good question. I don't know. I mean, I will claim ignorance here. I don't know what kind of groundswell, how we make this happen, how we convince the CIE. I am not plugged into the CIE committee. I'm plugged in, obviously, with all of the FTA committees. I think we need to find some group of people who are willing to take a lot of time on this to understand all of the trade-offs on the different functions. CCAM is a great color space, but it is very, very complicated. It allows us to predict how colors change when we change the background. So we change from a white to a gray background. Is that something that it makes the whole system more complicated? Is that something that we want to have in our color measurement? I think probably not. So we need a committee of people who are willing to put some time and head scratching into this.
Yeah, great answer, John. Just a couple reminders. You know, please, as you're leaving today, take that survey, give us some comments, and let us know what you want to hear in the future. Also, on Monday morning, check your email for the webinar recording, the link to the webinar recording, and that will be there. And then just, you know, a couple of reminders on upcoming events. If you're planning on entering the Excellence in Flexography Awards competition, you got a few days left. We need to have those samples to our office by January 25th. So, you know, everything you need to know is on our website. So visit flexography.org for more info on that, as well as the Technical Innovation Award. Have a little bit more time to fill out the intent to compete form. That is due February 16th. Also, I want to mention our next webinar is coming up in a couple short weeks, and that is Leadership at All Levels, presented by Alyssa Denny. And then let's not forget about the greatest Flexo show on the planet, Forum and InfoFlex 2024, happening in Kansas City, Missouri, May 5th through the 8th. Yeah.
Kansas City.
And with that, I'll let John sing us to a close.
They got some crazy little Flexo there, and I'm gonna get me some.
Yeah, see, people are leaving, John. John, thank you on behalf of
Absolutely
all of us at the FTA and the first committee and the FQC committee. We appreciate your insights here this morning. This was great. So thank you. Thank all of you for attending. John, there's people pumping out hearts and everything for you. So I think you did good, buddy. Thanks. Talk to you in that meeting this afternoon.
Bye-bye.
Bye, everyone. Take care. Have a great weekend.